Hi everybody, this is Mr. Mott, and I'm going to give you some notes on how to do phase change, how to do heat calculations involving phase changes. Okay, so what I've got here is I've got my phase change diagram, and my question is I've got temperature on the y-axis versus heat. Okay, and my first question is how much heat does it take to melt 100 grams of ice? Okay. So the first thing you want to recognize is where are you at in your phase change diagram, okay? As far as my phase change diagram here, I've got solid. This is solid plus liquid, liquid, and liquid plus gas. So if I'm in the melting stage, okay, that means I'm in this stage right here in this flat part here, okay? Now, when I go about doing these calculations, and I think about heat, I think about my heat formula. Q equals mc delta T. Now, during a phase change, what we want to think about is, we can know the mass of it, we know the specific heat that will be given. What is our change in temperature? And our change in temperature during a phase change is 0. Now, if I have a 0 for my change in temperature, what does that make my heat? Well, it makes my heat 0. Now, we need to ask ourselves, does that make any sense? Does it require 0 heat to melt ice? And we know that that's not true. We do need heat to melt ice. So we're not going to be able to use this particular formula during a phase change. Turns out we're going to have a different one. Okay, so we're going to use, formula is Q equals M times delta heat of fusion. Okay, now this looks even more confusing than our other formula, but actually it isn't. The delta heat of fusion, all of this together is a constant value, just like it is for a specific heat. It's just a constant that we give you, and so that's the formula that we're going to use. Okay. So my formula is going to be Q equals M times delta heat of fusion. Okay, and so plugging in our numbers, my mass is 100 grams. And the delta heat of fusion of ice is 334 joules per gram. So it means for every 1 gram of ice, it takes 334 joules to melt it. We can see our units with grams will cancel, and we're going to get 334 and add a couple zeros on there for our answer. And that's it. Kind of neat, huh? So during a phase change, our takeaway message is we need to use our different formula. Anytime there is a temperature change, we can still use our old school, our first heat formula. So you can use, whenever you're dealing in the solid area, you can use that whenever you're dealing in the liquid, or I forgot to write it in here for our gases. All right, for our gas. And anytime that you have a temperature change, you can still use this formula. Okay? Now we get to a situation where what if we have a different scenario here? So we're going to have to use a combination of methods. So my second question is, how much heat does it take to change 75 grams of ice? How much heat does it take to change 75 grams of ice to 75 grams of water at 35 degrees Celsius? Okay? So whenever you have whenever you're dealing with and you read the problem and you recognize it's a phase change, it's very helpful to draw a phase change diagram and then sort of plot and figure out where are you at in the grand scheme of things. All right? So if I'm dealing with, if I have 75 grams of ice, okay, that means I'm right here in our phase change diagram. And then 35 degrees of water would be somewhere up in here at 35 degrees. Okay, so this is kind of our start. And in this problem, we're actually going to figure this out on two different steps. We're going to calculate how much heat it takes to go from here to here and then here to here. And we're going to incorporate two different formulas. So the first one is that I'm going to calculate how much heat it takes to be able to melt our ice. I'm going to figure out the Q of the solid plus the liquid. So I'm going to use my Q equals M times delta heat of fusion. And we'll plug in, I got 75 grams times 334 joules per gram. Okay. So 75 times 334, we get 25050, and that's in joules. The second part of this equation, what I'm going to do is I'm going to figure out how much energy it takes. So what I've done so far is that I've melted the ice, and now I have 100% water. And so I'm going to say, how much energy does it take to increase the temperature of that water? So I'm going to say Q of the liquid now. And so I'm dealing with the temperature change. So I'm going to use my Q equals MC delta T formula. And so I still have 75 grams. We're assuming no loss of mass. My specific heat of water is 4.18 joules per gram degree Celsius. And your change in temperature is 35 degrees. Okay, so I'm going 75 times 4.18 times 35. So I get 10,972.5 joules. Okay. So now I figured out it took about 11,000 joules to go from here to here on our graph. So what are we going to do as far as to figure out the total amount of joules it took to go from 100% of solid to this 35 degree water? We're going to add these two together. So when you add these two together, 25050 plus 10,972.5, we're going to get 36,000 to 2.5 joules. Okay? That's not rounded to significant figures or anything like that, but that's the idea. So when you're dealing with phase changes, and heat calculations, just recognize you're going to be using multiple steps, and you're going to be doing so you got multiple steps of calculations there. You're going to have some different constants that you're going to need to know to use. And one thing I should tell you, for instance, let's go back up to our graph here, is that when you're dealing with Q equals MC delta T for your solid, for ice, you're dealing with a different specific heat. That's going to be 2.01 joules over grams degrees Celsius. Okay. For water, we know the C value of water anyway, but we're just go ahead and write it down here, 4.18 joules per gram degree Celsius. Okay. If we were to get up into the boiling stage, your formula is going to be a little bit different than here. It's going to be Q equals M times delta heat of vaporization. Okay. And the delta heat of vaporization, I think, is 2260 joules per gram, but that's a constant value that we're always going to give you. Okay? So that's how you handle heat calculations in with phase changes. And we're going to work with this a bit more, but that's kind of the general idea. All right? Thanks for watching.